Okay, so welcome to Math383 complex analysis. This is a supplemental lecture on probability. And so the goal is to try to explain one of the most important results in the subject, namely that if you have a bunch of nice random variables, then the sample average converges to being normally distributed. And so what do I mean by this? So I mean that the variables, I'll go a little bit lower. So we use capital letters like this to indicate this is the random variable, lowercase to indicate that it's a specific value. So we're going to assume these are independent, identically distributed random variables. Without loss of generality, the mean is 0, the variance is 1, and I'll assume the higher moments are finite. Okay, I'm not going to assume anything about how finite. Okay, so if I give you a random variable, if I look at some notation, so the expected value of g of x is the integral from minus infinity to infinity of g of x times the density of the random variable x. So this is the density of the random variable x. So typically, if we take g of x equals x, that's the mean. If we take g of x equals x to the k, that's the kth moment. We often let mu equal the expected value of x. And then the variance of x is the expected value of x minus the mean squared, which after some algebra, turns out it's the same as the expected value of x squared minus the expected value of x squared. So it matters where you put the squaring. And we'll often denote that as sigma squared. Notation matters. Since I'm defining it as sigma squared, what do you think is the object that matters? Sigma, right? So you normally don't name something sigma squared unless you really, really, really want to take a square root of it, right? So think about the notation. Okay, so these are some of the key concepts. Now, if I give you a nice random variable, we can always play the translation game. If x has mean mu, if we let y equal x minus mu, what's the mean of that? 0. And so you can just go through and do the algebra. If my average value is 7 and I subtract 7 from everything, my new average value should just be 0. The next is if x has variance, well, let's do standard deviation. Has standard deviation sigma, if y equals x divided by sigma, that has standard deviation 1. And here's the key fact. The expected value of a sum is the sum of the expected values. And then the variance of a sum is the sum of the variances if independent. Well, it makes sense that this should only be true if things are independent. Consider x1 plus x1. So here, x2 equals x1. Or x1 minus x1. And here, x2 equals negative x1. In the first case, I just get twice x1. In the second case, I get the random variable that's identically 0. So if my random variables have dependencies, I should not be able to figure out what's going on between them. And so whenever possible, you always want to do simple calculations like this to get a sense of what's going on. So the key thing is the variance of a sum is the sum of the variances if they're independent. Now, related to this, if I give you the variance of a1 x1 plus dot 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 plus an xn, that's the sum, k goes from 1 to n, of ak squared variance of xk. And if you think about what's going on for the variances, we're integrating, it'll be like the expected value of, say, a x minus the expected value of ax, whole thing squared. And that was, we said, the same as the expected value of ax squared minus the expected value of ax squared. And so now that's going to come out as an a squared expected value of x squared minus a squared expected value of x squared. So that's going to just be a squared, the variance of x squared. So the standard deviation of ax is just the absolute value of a times the standard deviation of x. That's the nice way to look at things. If I rescale, if instead of measuring things in yards, I measure things in feet, all of my numbers have just changed by a factor of 3. So my variance is going to be increased by a factor of 9. My standard deviation is going to be increased by a factor of 3. And so you just have to be careful that it's the absolute value that comes through, because we want things to be non-negative. So if I give you the variance of a sum or weighted sum, you have to square all the coefficients. So what this is basically saying is, if I have a nice random variable without loss of generality, what does its mean? 0. And without loss of generality, what's its variance? 1. So this is called the standardization process. And so, without loss of generality, just to make life easy, we can assume all means are 0, all standard deviations are 1. And let's study x1 plus xn. Now, if I didn't normalize to have mean 0, I would subtract off n times the mean. I don't need to do that. What is the mean of this? The mean is 0. What's the standard deviation?
N times.
It's n times each one. So it's just n. So what we want to do is we study x1 plus xn divided by the square root. Wait a minute, the standard deviation is square root of n. It's right here. It's the variance that's n.
Oh, right.
It's the variance that's n. So if we divide by the square root of n, then the variance of x1 plus xn over square root of n is going to be the sum, k goes from 1 to n, of the variance of xk over root n, which is going to be the sum, k goes from 1 to n. And now it comes out as a 1 over n because we square things, variance of xk. And then that's going to be 1 over n times 1, which is 1. So it is the square root of n that we want to normalize by. Okay, so this is a good quantity to study. So we want to study this. This has mean 0, standard deviation 1. So this is something that hopefully has a nice limit as n goes to infinity. So we want to look at the limit as n goes to infinity of Zn, where Zn is x1 plus xn over square root of n. And the central limit theorem is that Zn converges to being a normal with mean 0 and variance 1. Now, what's fascinating about this is that if I give you a probability distribution that's nice, without loss of generality, the mean is 0, the variance is 1, I don't see the shape of my random variable until I get to the third moment. If my random variable is symmetric, so the positive values, the value at x is the same as the value at negative x for the probability, then the third moment is going to be 0. All the odd moments are going to be 0. It's not until the fourth moment that I start to see the shape of the distribution. So when I'm looking at a probability, yes. Sure. So over here, the expected value of g of x is just integrating g of x against your density. And then the moments are the special case when g of x is x to the k. So when k equals 1, then that's just the mean. If the mean is 0, then the second moment is the same as the variance. But in general, the second moment is not going to be the same as the variance. And so they sometimes talk about the centered moments. So the centered moments is, instead of looking at the expected value of x to the k, you look at the expected value of x minus mu to the k. And so the hope is that if you know the moments, then you know the distribution. Unfortunately, or fortunately, you've taken weeks, months of complex analysis with me. And you know at this point that real analysis is hard, and that all of these results that you would love to hold don't. So we don't expect at the end of the day the moments to uniquely determine a distribution. It would be wonderful if that were the case. And the hope is that if I have a nice situation, then the sum of the x's divided by square root of n, this is normalized to have mean 0, variance 1. The hope is this will have a nice limit as n goes to infinity. It turns out the higher moments of the probability distribution only come into play in terms of how quickly it converges to being normal. This is the Berry-Essen theorem, that it's the third and the fourth moments that basically govern the rate of convergence. But the fact that we have this universal result, why does it not matter what distribution I take? As long as the distribution has finite moments, it's going to converge to normal. That's incredibly encompassing. Why the miracle? And the miracle is that without loss of generality, this is the source of the miracle. So miracle is because without loss of generality, mean equals 0, standard deviation equals 1. That's the source of the universality. So if this wasn't emphasized when you saw the central limit theorem, this should be. This is why we have this incredible universality. Okay, now we want to prove that this is the case. Okay, so I am doing this from memory, so bear with me. All right, so we have the density of my sums of my random variables. And I'll do this first without dividing by the square root of n. So this is going to be the n-fold convolution. So it'll be f of x1 convolved with f of xn, all evaluated at t. All right, well, if I want to put in a square root of n with each one of these, that's really not that big of a deal. I can just go like that. Okay, so now, how do I understand? Well, all you need to do is put in what f is, do the n-fold convolution, take the limit as n goes to infinity, and notice that that converges to the Gaussian. Good luck, right? Now, all of these f's are the same, but this is going to be an n-fold integral. You do not want to do an n-fold integral and take the limit. That's infinitely many integrals. One possibility is take the Fourier transform. Okay, and then we would get the Fourier transform of Zn of t is going to be the product k equals 1 to n of the Fourier transform of xk over square root of n at t. Why am I using k as my index and not I? Yes, this is a lecture in complex analysis, right? Do not use I as an index. Okay? Well, this is going to just be, they all have the same density, so I'll just call it f of x over root n at t to the nth power. So the Fourier transform of that. Okay, so I now just need to analyze this. All right, so now my next question is, if I understand, fx of x is a density, and I could let y equal x over a, and I can look at some new density fy of x. Maybe use y. And I want to figure out, how is this related to my original thing? So if I want to calculate the Fourier transform of fy at some input y, this is just going to be the integral y. I'll use maybe t goes from minus infinity to infinity of fy of t. I'm sorry. Yes, fy of t e to the negative 2 pi I yt dt. Is everybody fine with this as my definition? That's just the definition of the Fourier transform. Now, this is the same as the integral t goes from minus infinity to infinity. My density y is just x over a. Right? So I've got to figure out, how do I go from one to the other? So it's a change of variables. And we've got to make sure we do this properly. So it's going to be f, I can write it so like this, x over a of t e to the negative 2 pi I yt dt. That's clearly fine. I've just replaced y with x over a. But I want to figure out, how are they related? Well, the probability that y is less than equal to little y, this is called the cumulative distribution function. It's the probability I take on a value at most y. This is the integral from negative infinity to y of the density of y of t dt. If I take the derivative of this, so if I take d by dy of this, well, let's see, I've got an integral. So I'm going to take d by dy. I'll have the antiderivative at y minus the antiderivative at negative infinity. What's the derivative of the antiderivative? Yeah, just the function. So that'll just be fy of y. And the other piece is constant. So this is called the CDF method. If I want to figure out what is the density, if I can calculate the probability I take on a value at most a certain amount, then if I just take the derivative, that will give me the probability density function. Why am I doing this? Well, if I want to calculate the probability that y is less than equal to y, this is the same as the probability. So y is x over a. That's the probability that x is less than equal to a times y. Right? And so what would I get? So therefore, d by dy of the probability y less than equal to y would just be what? I'm sorry? So I would be taking the derivative, I would integrate from minus infinity to a times y of fx of t dt. So this would just be fx at ay. Correct?
Minus 8.
So this is not correct. You got to be careful, guys. So let's do it slowly. This would be d by dy of the antiderivative of my density evaluated at ay minus the antiderivative of my density evaluated at negative infinity. Now I take the derivative. So it's going to be the density at ay times the derivative of ay with respect to y, which is going to be an extra a. Okay. So that's going to be my density. My density of y is going to be my density of x at a y times a. So now if I go back to what I had over here, this would be the integral t goes from minus infinity to infinity. And then this is just the density of x at t over a times e to the negative 2 pi I yt dt. And then I also have an a coming in, right?
Why is t over a instead of at?
Oh, is it, I'm sorry, it's at, sorry, thank you. Okay. Does this make sense? So this is the Fourier transform of y is now related to the Fourier transform of x, but it's at a different point. All right, so that means we have to do more work. So this was f hat y of y. So let's continue to do the analysis. Let's change variables. Let's let u equal at. So dt is going to be 1 over a du. Or better yet, actually, I think I want to do it this way. Du equals a dt, because we actually have an a dt. So I can write this as the integral t goes from minus infinity to infinity, fx of at e to the negative 2 pi I. I'm going to write it as y over a times at times a dt. And now wherever I see an at, I can replace that with a u, and an a dt, I can replace that with a du. So this is going to become the integral u goes from minus infinity to infinity, fx of u e to the negative 2 pi I y over a u du. What does that integral equal? The Fourier transform of the function x at y over a.
Oh, yeah.
If y equals x over a. Okay, so for example, if we have the Fourier transform of x divided by square root of n at t, that'd be the Fourier transform of x at t over square root of n. So, again, you've got to do these calculations slowly. But in principle, I hope you see that this is not a tough calculation. It's just chasing things down and not making a mistake. But it's just, constantly changing variables so that I can express the Fourier transform of the density Fy in terms of the Fourier transform of the density of x. And y is just rescaling things. So it makes sense that they should be related. This is how they're related. Okay, now that I have that, I can go back a couple of pages and we had this result. And so I was actually talking with one of my colleagues recently about, is it good or bad that we have switched to doing a lot of things on iPads? It's nice when you have a whole blackboard with things that you can stare at. But at least if it's now done like this, I can quickly go back to a previous screen and say, this is what we had before. And so now let's take what we had before. And so we'll put, so it didn't work. All right. So hopefully my memory works then. We had the Fourier transform of z at t was the Fourier transform of x over square root of n of t to the nth power. But from what we just saw a moment ago, this is the Fourier transform of x at t over square root of n to the nth power. Right? We just proved a moment ago. All the f should have hats, yes. So we should, yes, they should definitely have hats. It's cold. All right, so do we all agree that we have this now? Now, this is progress. Why is this progress? Well, let's look, f hat of, I'll use y. Is it okay to use y here? You want me to use y not? So this is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. When in doubt, assume that there's very little you can do in life and milk it for all it's worth. What value of y would make your life easy? 0. If y equals 0, f hat of 0 is just the integral from minus infinity to infinity of f of x dx. What does that equal? It just equals 1, right? Because we're integrating a probability density as f is a density. So I've been using subscripts x's. I'll put the x's back in. So we agree that we understand what the Fourier transform is at 0. What if I give you the Fourier transform at a point really close to 0? What should it be close to? 1. Wouldn't it be wonderful if we were only evaluating the Fourier transform near 0? Ooh, look, we're only evaluating the Fourier transforms near 0. We have the Fourier transform evaluated at t over square root of n, we're then going to infinity. So as n gets really, really large, we're essentially evaluating it at 0. So what is f hat of x at t over square root of n as n gets very large? It's approximately 1. And so when you raise it to the nth power, it's the Gaussian. Huh? Okay, it's not exactly 1.
Yeah.
We need to quantify how close is it to 1 as a function of n. And if we can quantify that, maybe we can then understand the limit as n gets larger and larger and larger. If we just replace it with 1, 1 to the n is 1, and no, okay. But again, I'm trying to give you big picture what's going on. All right, so let's make some more progress. So we have the Fourier transform is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. If I let y go to z, do we agree that it's holomorphic? At least in a small neighborhood of the origin. Assuming my function has sufficient decay, everything should be fine, right? I might need to have some kind of decay, but the hope is that things will be good. What do we know about holomorphic functions?
Accumulation.
There's that, but
Are you doing a conference?
there's that, but I'm using the word holomorphic. Analytic. Holomorphic functions are analytic. So I should be able to write this maybe as, this is the Fourier transform. This should be the Fourier transform at 0 plus the Fourier transform at 0 times y plus the Fourier transform, I'm sorry, no, the derivative of the Fourier transform at 0 times y plus the second derivative of the Fourier transform at 0, y squared over 2 factorial plus dot, 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 dot. Yeah. If my function f has finite support, then this is clearly going to be doable. If f is bound, it lives in a bounded interval, there's no problem. If f is a Gaussian decaying rapidly, there's no problem. if f has exponential decay, this will be fine as long as z doesn't have too large of an imaginary part. I can get holomorphicity in some interval if my function has sufficient decay. And holomorphic really means analytic. So I'm going to calculate a Taylor series expansion. I need to calculate the derivatives. And now we use our physics hat, right? What is the derivative of the Fourier transform? Well, I would just integrate from minus infinity to infinity of f of x, and I would have negative 2 pi I x e to the negative 2 pi I xy dx. I can pull out a negative 2 pi I, right? And I have the integral from minus infinity to infinity of f of x. I'm going to put the x over here, e to the negative 2 pi I xy dx. So what would the derivative at 0 equal?
Would
be
the derivative of the Fourier transform, which means that there's a hat.
Oh, yes, yes, there should be hats here. Yes, thank you. I'm dropping a lot of hats today. All right, so what should this be at 0? It's just negative 2 pi I times the integral from minus infinity to infinity of x, f of x dx. And I've dropped my subscript x. I'll put that in the function. What is that integral equal to? 0. It's the expected value of x, which is 0. Let's look at the second derivative at 0. I hope you all agree that after some algebra, you would get 4 pi squared with a minus sign. Because I would just have another derivative coming down, and I would have the integral from minus infinity to infinity of x squared times f of x dx. So that's going to be negative 4 pi squared times the variance of x, which is just negative 4 pi squared. Now, what does the Fourier transform of f at 0, what does that equal? 1. What does the Fourier transform derivative at 0 equal? 0. And what's the second one's going to be minus 4 pi squared.
Why is the Fourier transform at 0
Equal to?
Like at
we just did that a moment ago. That's the easiest point to evaluate the Fourier transform, right?
It's just the expected value.
It's just the expected, right? So this is why we often talk about the moment generating function. And there's such a connection between the characteristic function, the Fourier transform, and the moment generating function. Okay. Look at the Taylor series. It starts off with 1. Great, because we know when the input is near 0, it should be 1. The linear term is 0. Good, so if we don't move that much, then the next term is going to be negative 4 pi squared. Okay. So now, yes.
So if we want to make the derivative of this Fourier transform like rigorous, do we need to use like accumulation theory to show that these are the same?
No, I mean, we just need to justify differentiating under the integral sign.
Right.
We need to justify that there's a series expansion for the Fourier transform.
No. Like when didn't you say we need to use the physics mind?
Oh, the physics is just interchange the derivative and the integral.
Oh.
Right. A good physicist, might snort and just keep moving. An economist would go, we need to justify that? At least the physicist realizes, oh, this is being recorded. I should speak more slowly for the economists. So a mathematician would pause and worry, can we justify interchanging the derivative and the integral? That's what we need to do. We want to pull the integral the derivative inside the integral, take the derivative of the exponential piece. And there are theorems that allow you to do that in real analysis. I'm not going to go through those now. I'm trying to give you in less than an hour, the proof of the central limit theorem.
Okay.
And this lecture was prepared as I walked, home from lunch. I mean, I've done this for so many years that I should be able to do this quickly. I've been doing this longer than you've been alive. So I should be able to do this without too much practice. Okay, it's just, can I do it without making any algebra mistakes? So when we look, we have this analytic expansion. It's 1 plus 0y plus minus 4 pi squared y squared over 2 and so on. But we don't evaluate the Fourier transform at y. Where do we evaluate it at? Nope. Where were we evaluating things at?
T over.
T over. But we have your fx at t over square root of n hat to the nth power. So that should be 1 plus 0 minus 4 pi squared, and then y squared over 2 is going to become t squared over 2n. Right? Plus dot, dot, dot to the nth power. Okay? Let's think about what's going on with the dot, dot, dots. The next term, we're evaluating a t over square root of n. So the next term is going to be something like t cubed over n to the 3/2. And then the next term will be t to the 4th over n squared, and so on and so on and so on. I claim those terms don't really matter. Let's see. How should we understand this expression to the nth power?
It's just e to the x with some other stuff in there.
Right, but we got to be careful. So how should we understand this? I'm sorry? Nope.
There's some formula for like e to the x.
What should we do? Take the logs. Whenever you see a product, what should you do? Take the logs. So I checked, I'm not allowed to give you shocks, unfortunately. Whenever you see a product, take a log, okay? If see product, then take log unless with young kids. Okay? Definitely 4th grade. Okay, whenever you see a product, you should be thinking, take a logarithm. So I can go into much greater detail about how it's very easy to miss some factors. So if we take our expression like this, let's hope I can copy it this time. Nope. All right. So we have the log of f hat of z of t is going to be n times the log of 1 minus 4 pi squared t squared over 2n plus terms of size t cubed over n to the 3/2. Is everybody comfortable with if I just write it at that level? Now you have to worry about, we have terms of size t cubed over n to the 3/2, then t to the 4th over n squared, then t to the 5th over n to the 5/2. And you just have to show that if I sum all the stuff from here onward, it's going to just be something of size t cubed over n to the 3/2. Okay. Now, what is the log of 1 minus u? That's going to be minus u squared over 2 minus u cubed over 3 dot, dot, dot. So we have n. Now what's u? So the first piece is going to be minus 4 pi squared t squared over 2n plus terms of size t cubed over n to the 3/2, right? That's the first piece. what's the next piece going to be? It's going to be that whole thing squared. So this is going to be stuff of size 1 over n squared. Right? Because if you look at the net, we start off with 1 over 2n. So when we square, it's going to be something of size 1 over n squared. And so as you go further and further and further down, it's going to be small and small and small. So when I multiply through by n, I'm going to get negative 4 pi squared t squared over 2. Okay, so that 4 becomes a 2, right? And then I'm going to have something of size, t cubed over square root of n, plus something of size, 1 over n plus dot, 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 dot. And this is where I'm being a little bit careless in terms of our analysis, that all of this stuff doesn't really matter. But the whole point is, as long as all these sums converge, t is a fixed number. As n is getting larger and larger and larger, all of this other crap is just going to go to 0. And so we're going to be left with negative 2 pi squared t squared. So if the log of f hat of z of t goes to negative 2 pi squared t squared, then fz of t hat is going to go to e to the negative 2 pi squared t squared. Yes.
Is this pointwise convergence? Because it seems that we have fixed t.
So we fixed a t.
So that's going to be pointwise convergence.
So it's going to be pointwise convergence. And then you can start talking about, is the convergence uniform if t is in certain ranges?
Wait, so in the central limit theorem, it's not uniform convergence, it's only pointwise convergence.
I don't want to get into, there's like 4 different types of convergence you can get into.
Oh.
And I'm not going to get into enough detail here in 1 hour to get into all the different types of convergence. There's pointwise convergence, there's L1 convergence, there's L2 convergence. There's also convergence where if I integrate against a test function, then the integrals are the same. There's lots of different types of convergence you can do. Basically, this is showing that pointwise, it looks like the Fourier transform is converging to e to the negative 2 pi squared.
Okay, got it. Why do we have f hat z of t instead of t over square root of n?
Because we're evaluating z at t, and then that's related to all the other ones at square root of n when we adjust things. Because we have the sum of the random variables at t. So z is just all the x's divided by square root of n.
Okay.
And I guess I've been calling that f z sub n. I think I dropped a minus sign somewhere, so I'm just double checking something right now. And so when we look at what's going on, okay, so that's a negative.
You took this derivative again for the second one. Why didn't another negative I cancel out the other thing? Oh,
Because we have an I squared.
Yeah.
And so I think that is supposed to be a minus 4 pi squared.
Technically, if we take the second derivative, we get another term where because we have to take the derivative of x by the product rule, but does that?
No, because we're taking the derivative with respect to y.
Oh.
We're taking the derivative with respect to y. That's why another factor of 2 pi I x negative 2 pi I x comes down. And so that should be a negative 4 pi squared. Okay, so that's definitely a negative 4 pi squared. So we have a 1 minus u.
But for the 1 minus u, isn't the series alternating instead of all negatives, right?
No, it's 1 plus x that's alternating. 1 minus is all negatives.
Oh, I think we made a mistake on the power series expression. So we have to take the negative of negative 4 pi. I guess minus u cubed over 3.
Well, but I'm writing it as my u is basically 4 pi squared t squared over 2n.
Is it like negative? Oh wait.
No, because so u is 4 pi squared t squared over 2n. And so I mean, it should be, I believe, e to the 2 pi squared t squared, not an e to the negative 2 pi squared t squared. I think we're off by a minus sign somewhere and some normalization factors. But morally, this is what's going on. And this is where the central limit theorem now comes from, is that this should basically be the Fourier transform of a Gaussian. And so it's just some normalization conventions and whatnot coming from, I think, factors of 2 pi. Oh. So first of all, maybe there's not supposed to be the 2 pi here, because when we're doing things with characteristic functions, we don't have the 2 pi's, right? The characteristic function doesn't have the 2 pi. It's not quite the Fourier transform. So we should be getting rid of the 2 pi's. And so that's going to get rid of some of that. Okay. But it seems like we have an extra.
So then wouldn't that just give us negative t squared over 2? Isn't that what we want then?
Right, but I think we want positive t squared over 2. Because I think the Fourier transform of the Gaussian is e to the t squared over 2, not e to the negative t squared over 2. And so there's a minus sign error somewhere.
In class, didn't you have the Fourier transform of the Gaussian negative t squared over 2?
Okay, well, but what did you check? Does it have a minus sign or a plus sign?
It has like a constant and minus sign.
Okay, so maybe it's correct. Okay, and so, all right, so if that's correct, then basically what we do is the following now. We have e to the negative 2 pi squared. Oops. We have e to the negative 2 pi squared t squared, which is e to the negative 2 pi squared t squared over 2. Get rid of the 2 pi in the Fourier transform to use the characteristic function. And that yields basically e to the negative t squared over 2. And so basically something along these lines is what you need to finish the argument. So this is one way to use complex analysis to prove the central limit theorem. And this was basically about an hour. You have to do a little bit of work to justify everything. You need to know what is the Fourier transform of the Gaussian. And I thought, but what I might be mixing up is, oh, wait. I'm mixing it up. The moment generating function of the Gaussian has a positive sign, but the relation between the moment generating function and the Fourier transform is an extra factor of I. And when you square I, that's the -1. And that's why in my mind, I'm off by a minus sign because I'm thinking of the moment generating function, which differs by an I squared. And there we go. Okay, so everything is good, math is consistent. And now we're basically getting exactly what we should.
Wait, so the only place where we use complex analysis is when we said this X
Is analytic, is holomorphic, is analytic. So that was the big place. I mean, to some extent, we're using it in many places whenever we're doing a Fourier transform or a characteristic function.
Okay.
But yes.
When do we make so we assume that the higher moments behave nicely. When do we use that?
Many times. Whenever we have things like this, and I say ... you can handle all that, I need some control over the sum of those terms. If the moments are exploding so that things are not finite, then those sums would blow up. And I've got to make sure that those sums are finite. And so if the moments are not too large so that the sums converge, then everything is fine. That's where we're using the finite higher moments. And that's exactly the type of question you want to ask is, when do we use this stuff? Do we really need it? Yes, we need it so that when I put in this dot dot here, I can use the big O notation properly and say, what is the contribution if I sum from the tail onward? And then as we start doing the Taylor series expansion, the u squared over 2, the u cubed over 3, my u is, this is my u from here onward. And I want to say the u squared over 2, the u cubed over 3. I want to say all that stuff doesn't really matter. Most of it's going to be controlled by the first term. And then you just show all the other stuff inside the u is a really small contribution relative to the first. The first one is of size 1 over n. The next is of size 1 over n to the 3/2. It's 1 over square root of n smaller. So as long as the sum converges, you then are dividing by a square root of n. So in the limit, it's going to be negligible relative to the main thing. As an aside, just to warn you about some things. What is the limit as n goes to infinity of 1 plus or minus x over n to the n? Okay, so what's the limit as n goes to infinity of 1 plus x over n to the n squared? Let's see, 1 minus x over n to the n squared. Well, this would just be the limit as n goes to infinity of 1 plus x over n to the n to the n, 1 minus x over n to the n to the n. Where does this piece go to? This goes to e to the x to the n. This goes to e to the negative x to the n. And so what should this product go to? Should go to 1.
So when you evaluate this differently, if you associate them together, like
so if I write it as this is the same as the limit as n goes to infinity of 1 minus x squared over n squared to the n squared, that's just e to the negative x squared.
so you can't exchange the order.
Well, what the hell am I doing? I'm writing n squared as n to the times n. And here, what I'm saying is, I want to take the limit of the whole thing. I'm going to just take the limit of just this part and keep n fixed. Let this go to the limit of e to the x, and then I'm going to bring back n. Then I'm going to do the same for the other part over here. Then I'm going to multiply, and then I'm going to let n go to infinity. You can't do that.
Okay, so the first method is correct.
This is correct. And this over here is, wrong. Right? But there's lots of people who make arguments like this. Let me try to break it up. And n squared, I can write that as n to the n. I know that this piece is going to get really, really close to e to the x. And this piece is close to e to the x. And the second piece is really close to e to the negative x. But when I raise it to a huge power by n, if it's off by just a little bit, it can accumulate. If you're off by a really small amount and you cube it, it's not a big deal. But if you're off by a really small amount and you raise it to the nth power, that's now enormous.
So it's like one of your faulty proofs by induction.
Yes. No, I'm proud of this one.
Oh, wow, why is the first one correct and the second one wrong? It's like technically it would be like
You can't take limits of just parts of things, right? This violates the 13th, 14th, and 15th Amendments to the U.S. Constitution. You must treat all equally. You can't just take the limit of part of the expression and then take the limit of the other part of the expression and then combine them and then take the limit. No, I can't do this, right? Because I have two different ends here and I'm just letting this end go to infinity and keeping that end fixed. And then I'm bringing it in. So I have to keep track. I'm going to stop recording now. I want to say something.